Okay, I hope you're sitting down for this definition, much like I had you sit down for the definition of a linear function. A quadratic function is a function of this format, f of x, that's our function notation, and the expression is going to be ax squared plus bx plus c. That's definitely a mind-blown fact right there, isn't it? Let's see if I got an emoji I can put in the chat for you. There we go. All right, so that expression should look familiar. Now, we've been working with those expressions for quite some time in this course now. But these expressions, quadratic equations, anytime you graph them, they will always pass the vertical line test, meaning that any quadratic equation can be thought of as a function. So much like we did with the linear equation, we're going to study them from the context of functions now. So all of that material that we learned in Chapter 3 can be applied to these functions, and we'll see a lot of that material creeping into our notes from here on out. The domain of any quadratic function is always going to be all real numbers. And the reason for that is much like the linear function, there's no way to divide by 0 in the expression ax squared plus bx plus c, and there's no square roots of negative numbers possible. So you can literally plug in any number you want in for x, and you're going to get a real number output. So domain is all real numbers as a result. Now, there are two forms of quadratic functions. The one that I have in the box right here is referred to as the standard form of a quadratic function. And on the next page, when we get to it, I'll present to you the other form known as vertex form. But before we do that, I want to give you some details regarding the graphs of quadratic functions. So you may have heard of this word before, parabola. All right, you probably heard that word. If you're a Tool fan, the rock group Tool, they have a song called Parabola. But you may have also heard of it, in an earlier course when studying the graph of a quadratic function. So a parabola is basically a U-shaped curve, and in this section, the U can face in one of two different directions. Okay, and that direction is based on the leading coefficient of a quadratic function, which is indicated by the letter a when looking at ax squared plus bx plus c. So this number right here, this number a, that's going to tell us the direction in which the parabola faces, or a different way of saying faces is the direction in which the parabola is opening. So a parabola can either open up or open down, and that will depend on the value of a, specifically whether it's positive or negative. So if a is positive, that is if a is greater than 0, we're going to have a U-shaped curve that opens up. And I'll give you a little sketch representing a U-shaped curve pointing up. If the value of a is negative, we're going to have a U-shaped curve or parabola that opens down. So I'm going to pick on the parabola that opens up to help us fill out the rest of this table. And the next row it says the parabola opens, and we would consider this opening up. And another way of describing how this parabola opens is by saying that it's concave up. Now, one interesting thing about parabolas is depending on how it opens, it's either going to have an absolute maximum or absolute minimum. So in the case where a is positive, and we're looking at our U-shaped graph that is, or our parabola that's opening up, which one of those do you think it might have, an absolute maximum or absolute minimum? Well, if we look at these arrowheads, that indicates that the ends of the graph continue going up and up and up. So it's actually, yep, it's actually going to have an absolute minimum. So there's a lowest point on the graph. And because there's a lowest point on this graph, we would say that this parabola has an absolute minimum. I'll say ABS min for short. And tying in some more chapter 3 material, if we place our finger on this end of the graph and we trace the graph going from left to right, the parabola decreases until it gets to this lowest point. And then once we go beyond this absolute minimum, or that lowest point, the rest of the parabola increases. So we can kind of describe its behavior, as such. The parabola decreases, and then it increases. So looking at the next parabola, the one that's opening down, another way of describing that is by saying it's concave down. And basically concave is like, if you were to try to form the U-shaped curve with your hand, it's kind of like cupping a little bit. So like the parabola with the value of a greater than 0, it's kind of like you're cupping upwards. In fact, if this were kind of like a side view of a cup, you could kind of fill it, the first parabola, but the second parabola, good luck with that. It's just going to go all over the floor. But anyway, that's kind of the idea of concave. How is it kind of bending, or how is it kind of cupping? And in Calc 1, you spend a little bit more time discussing what's called concavity in more detail. But for now, you can just kind of, think of these as like the equivalent of saying opens up or opens down. Now, whereas our first parabola had an absolute minimum, this parabola, the one that opens down, is going to have an absolute maximum because there's a highest point on it. So we'd say this has an absolute max. And if you start on the left end of the graph and you trace your finger along the parabola going from left to right, you would find that the parabola begins by increasing. So the parabola increases and then decreases. So far, so good? Now we're going to continue adding more details to this table, but we'll do that as we come across more terminology. For instance, if we look down here where it says key terms, the lowest or highest point on the parabola is called the vertex. So if we look at our parabola opening up, that lowest point, that absolute minimum, is considered a vertex. Even if there's a highest point, that highest point would also be called a vertex. So every parabola has a vertex, and it's actually one of the most important things about a parabola, and we'll see that when we do some applications. A parabola also has a natural line of symmetry. Specifically, any parabola is symmetric about a line that passes through this vertex. And the line that passes through that vertex is called the Axis of Symmetry, or AOS for short. Not to be mistaken with POS, by the way. So let me show you what I mean by AOS. I'm going to go to the first parabola, and I'm going to draw a dashed vertical line going through the vertex. That's what we mean by Axis of Symmetry. Okay, it kind of splits the parabola up into two equal parts. And you can draw an axis of symmetry with the parabola that faces down as well. On the next page, we'll actually look at formulas for both the vertex and the axis of symmetry. But before we do that, there is a way of predicting how many X-intercepts a quadratic function will have. In other words, how many times that a parabola intersects the x-axis. And you may recall this expression right here, b squared minus 4ac. That's the determinant of the quadratic formula. And in terms of values that it simplifies to, we can kind of classify those values in 3 different ways. For instance, if b squared minus 4ac happens to be positive, then the parabola will actually intersect the x-axis 2 times, meaning that the graph would have 2 x-intercepts. If the value of b squared minus 4ac zeroes out, then the parabola is going to intersect the x-axis just 1 time. And if the discriminant winds up being negative, you're going to get imaginary values as your solutions, in which case the parabola will not intersect the x-axis. So let me kind of draw some micro diagrams here for you. If b squared minus 4ac is positive, this would be a parabola, in which case the quadratic formula would have a value of b squared minus 4ac being positive, i.e., that graph would have 2 x-intercepts. A parabola having only 1 x-intercept is basically a parabola where the vertex is on the x-axis. So you might see something like this, where it looks like only one part of the parabola touches the x-axis, in which case that'd be the vertex. And we would qualify that as a parabola having just 1 x-intercept. And last but not least, we could have a parabola that doesn't intersect the axis whatsoever, in which case that would be equivalent to a quadratic function having a negative discriminant. All right, more information coming your way, folks. We can actually predict where the location of the vertex is at. And once we figure out where the vertex is at, we can quickly generate the equation for the axis of symmetry. So let's assume that our quadratic function is in standard form. Then the vertex can be expressed a couple of ways. Number one, oftentimes the vertex uses these letters as the x and y coordinates, h and k. And there are formulas for each of these, which I'll present in the next set of parentheses. The formula for h is negative b over 2a. Anybody seen that expression before, negative b over 2a? Just curious. Yeah, actually, you know what? This is a little chunk of the quadratic formula, believe it or not, negative b over 2a. Just so it turns out that if we can identify the a and b value in the quadratic function, we can use this formula to figure out the x-coordinate of the vertex. Now, the y-coordinate of the vertex k is what you get when you plug negative b over 2a into your function. Okay, so these two guys are definitely worth a flashcard. And we'll be using them quite a bit throughout the rest of today. Now, the axis of symmetry is that vertical line that passes through the vertex. Now, because it's a vertical line, the equation would be in the format x equals. And since it's going through the vertex, it's going to cross the x-axis at the value of h, as we'll see when we go back to page 1. So the axis of symmetry is always given by the x-coordinate of your calculated vertex. I'll just put x equals h. what also is cool about these formulas is that it gives us a way of rewriting our quadratic function into something called vertex form. And the vertex form of a quadratic function goes like this. F of x equals a, open up a set of parentheses, x minus h quantity squared plus k. So you'd be able to rewrite a quadratic function that's in standard form pretty quickly into vertex form by knowing the value of a, which is the same a that's in front of x squared, using the formula to get your value of h, and then using the second formula to get your value of k. And one nice thing about vertex form is that it's good for transformations. I just want to note that. I'm going to go back to page 1. And add a little more detail to both these parabolas. So let's look at the first one. And here I have pointed out the vertex, which the vertex we now know has coordinates h comma k. So that means right underneath this point on the x-axis, the value of the tick mark that corresponds to it would be given by h. And that's also the same spot on the x-axis where the axis of symmetry crosses. On the y-axis, so if we go back to this point and we travel over to the y-axis, that tick mark right there would be the value of k. And in application settings, this value of k would be the absolute minimum of our function. Can you tell why? It's the smallest value, the smallest y value that the function produces. So there are no points that get any lower than the vertex on this version of a parabola. So that would actually be the absolute min if we want to be a little more specific. Now the parabola opens down. Again, the vertex given by the coordinates h comma k. So directly underneath the vertex on the x-axis, we could put a tick mark of h. Again, the line of symmetry or axis of symmetry coincides with it. And then to the left of the vertex on the y-axis, we can put k. And in this setting, k would represent our absolute max. All right, let's get to some examples. So for our first example, we want to determine the vertex and axis of symmetry. So we have two things on the docket here. Let's start with the vertex. So the vertex is going to require both a calculation of the x and y coordinates. And in order to get the y coordinate, you're going to need to know what the x coordinate is first, because you plug it into your function to get the y value. I usually break this up into two separate workspaces. The first workspace is for our value of h, and then the second workspace is for our value of k. And then once we simplify these to just a single number, we have our x and y coordinates, and we can move on to part 2. Now h is given by the formula negative b over 2a. And the values of a and b come from our function, much like when we do quadratic formula. Does anybody want to type in the chat what our value of b is? Yep, our value of b is 6. And what's our value of a? Yep, negative 4. So we're going to basically just plug those in, much like any other formula. and I'll use parentheses. So -6 on top, and on bottom, 2 times -4. Now, I do want to share with you a little tip. In the denominator will always be multiplication of 2 times a number. And if you type this into your calculator, you can actually get 2 different results based on the usage of an extra set of parentheses or not. So I want to show you on my graphing calculator what that looks like. So let's say we had -6 divided by 2 times our value of a, which is -4. That's going to give you 12. And 12 is actually the incorrect value of h. And here's why. When your calculator reads this syntax, it does its best to follow the order of operations. Your calculator sees this of division at first, and then multiplication. So without an extra set of parentheses, your calculator is going to divide -6 by 2, and then multiply that result to -4. So it's doing behind the scenes -3 times -4, which is why you're seeing 12. 2 times -4 is all in the denominator, but the way it's typed out here, the calculator doesn't realize that. So the way around it is to use an extra set of parentheses. Now type in 2 times -4, and then close off each set of parentheses. And this is going to give you 0.75, which is our correct value of h. However, I would prefer the value of h in this example to be a fraction. And there's a way of converting your decimal to a fraction simply by pressing the math button. You select option 1 from the math column. It takes you back to the home screen, and it just shows you where it's going to get its next calculation. It's saying that it's taking your most recent answer, which is 0.75, and converting it to a fraction. Press enter, and you get 3/4. Right? Does anybody need me to repeat any of that? Our value of h simplifies to 3/4. To get our value of k, what we do is we take this value of h and we plug it into our function. All right, because remember, function notation is just a fancy way of saying that this is the y value with this particular x value. And so anywhere that we see the variable x in our function, we'll replace it with 3/4. So that'll be -4 times 3/4 squared plus 6 times 3/4 minus 1. All right, I'm going to give you a moment to type this into your graphing calculator. Don't forget the minus sign in front of the 4. And then see if you can convert your answer to a fraction and throw it into the chat bar once you get it. All right, so do we have confirmation on 5/4? Anybody else getting 5/4? Yep. So it should be 5/4. Okay, that's what f of 3/4 simplifies to. Well, these are both the values of h and k, so our vertex I'm going to write as an ordered pair. Our value of h is 3/4, and the value of k, which we just calculated, is 5/4. Now the second part of this problem wants us to provide the axis of symmetry, or the equation for it. Take a peek a little bit above the example verbiage here. It says that the axis of symmetry equation is given by x equals h. And this h right here is the same h that we calculated in part 1 of this problem. So x equals 3/4. Can't get any easier than that, folks, eh? That would be the equation for the axis of symmetry. All right. Any questions about this example? All right, so we're going to put a little spin and mix a vertex calculation with a little bit of conceptual understanding about maximums and minimums as it relates to parabolas. In our upcoming example, it says determine, without graphing, whether the given quadratic function has a maximum value or a minimum value. And once we do that, we're going to provide the value of whatever one this function would have. So this is kind of another two-parter. Okay, we're going to determine whether it has a maximum or a minimum value, and then we'll find the value. Now the first part is actually quick and easy, as long as you understand the concept of the orientation of the parabola. This first part can be answered by looking at the a value of the quadratic function. Our a value is +1, which this means that we have an a value that's greater than 0. So what would that mean about a parabola? Would that be a parabola that opens up or opens down? Right. So anytime your value of a is greater than 0, your parabola is going to be a parabola that opens up, or in other words, is concave up. Now, why is that important in terms of answering whether it has a maximum or a minimum? Well, let me ask you this. Would this parabola have a highest point, or would it have a lowest point? It would certainly have a lowest point. And because there's a lowest point, this function is going to have a minimum. Does that make sense? Now, the minimum is the location, or is related to the location of that point, in other words, the vertex. Specifically, the minimum value of this function is going to be our value of k. Okay, so in this context, we're looking for the smallest y value that the function produces. And since this is a parabola that opens up, our smallest y value is going to be the y coordinate of the vertex. So I'm going to kick this off to you guys, the second part here, where the strategy is to find the vertex. So that's going to require a calculation of h, as well as a calculation of k. right, so I'll give you a couple minutes to work on that. And once that's over with, I will check in to see how we did. All right, I'm going to show you my work for H. Note here that our value of B is -6. So that'll be -6 on top of 2 times 1. Extra set of parentheses just for good practice. And we're looking at 6 over 2. Did we get a value of H as 3? Rock on. Now for the value of K, we're going to take this 3 and plug it into our function. Okay, so our function is x squared minus 6x plus 5, so that means we'll have 3 squared minus 6 times 3 plus 5. This can be worked out by hand. 9 minus 18 plus 5. You probably got -4. Right? So in the context of this problem, I'm going to say minimum value is given by K, which is -4. All right. Does that look good to you folks? Cool. Now, I do want to include a little note somewhere where I can fit it. Let's see. Yeah, probably right here. We have 3 special values in this problem. We have a value of A, which is 1, calculated H, which is 3, and we also calculated K, which is -4. You can bundle all 3 together and put them, or put this function into vertex form versus standard form. So currently, it's in standard form, the x squared minus 6x plus 5. Vertex form says that you take the value of A, which in this case is 1, multiply it to a set of parentheses, in which case it's x minus h, so x minus 3 quantity squared plus k, and that simplifies to x minus 3 quantity squared minus 4. That right there would be the vertex form of this quadratic function. Now, the reason why I'm mentioning vertex form, because I made a note earlier that vertex form is good for transformations. And here's what I mean by that. The quadratic function is based on a library function, and that library function would be x squared. And if we want to, we can sketch the graph of f of x based on the graph of x squared, which I just put in the coordinate plane as a dashed graph. Think in terms of transformations, right? The value of a, if it's greater than 1, will tell us to stretch the parabola, and if the value of a is less than 1, we would have to compress it. Now, our value of a is not different than 1. It's 1 itself, so this parabola wouldn't stretch or shrink. And there are no negatives in front of the parentheses or in front of x, so no reflections. However, there is an indication of both a horizontal and vertical shift. The fact that we have x minus 3 inside the grouping symbols would tell us to move the graph to the right by 3. And then what's the second transformation? Down 4. Yep. So I'm going to do both at the same time. I'll put 3 tick marks on the x-axis, positive part of it, and then 4 on the negative part of the y-axis. And the origin, 0, 0, would move to 3, negative 4. And there would be no other transformations, so I'm going to go ahead and include this as a bold graph. And what do you notice about 3, negative 4? What special part of a parabola does 3, negative 4 represent? Three, negative 4 doubles up as our vertex, right? So we calculated the vertex using some formulas. If we were provided maybe the vertex form of the function instead of the standard form, we'd be able to identify where the vertex is at simply by doing transformations. Well, that's kind of one of the benefits of vertex form. And in my opinion, it's probably the biggest benefit. But either way, it's kind of a mind-blown thing going on there. Okay. We are going to do what's called analyzing a graph. And this is where we kind of throw all of our weapons at providing the sketch of a function. In this case, it's going to be a quadratic function. A quadratic function in standard form. Now, we just saw an example of how we could graph a quadratic function provided in vertex form, but it's not always feasible or very easy to transform, well, not transform, but rewrite a standard form into vertex form. And plus, when you sketch things using transformations, it's really just that. It's a rough sketch, so it's not really extremely accurate. When we throw some of our skills from chapter 3 into graphing a function, that's pretty much what we refer to as analyzing the graph of a quadratic function. And this is a skill that we'll be doing with polynomials in chapter 5 and more intricate functions, if you will. Basically, we try to apply all of our algebra skills to figure out information about a graph, and when we translate that into the coordinate plane, we get a pretty darn accurate sketch of a function. So we're going to do that with f of x equals negative x squared minus 4x plus 5. And you can see there's a whole bunch of different parts to this problem, but don't be scared. A lot of these parts go by pretty fast. But they all help us to get an idea of what this graph would look like from an algebra standpoint. And like I said, once we translate it into the coordinate plane, we get a very good, very accurate sketch of this function. So in part A, they want us to identify how this parabola is going to open. And we can predict that just by looking at the value of A, which is negative 1. So A is negative 1. which means that a is a value that's less than 0. So how should our parabola open? Should it open up or down? Yep, should open down. Part B wants the vertex. Okay, so I'm going to kick this off to you again. Calculate the value of h, and then use h to calculate the value of k. All right, so our value of b is -4. So to calculate h, we're looking at -4 all over 2 times -1. Did we get h equals -2? Sweet. We can actually knock out the axis of symmetry at this point. The axis of symmetry is always x equals the value of h. So that's kind of a quick and easy one. Now to find the value of k, we'll plug this -2 into the function. So -2 squared minus 4 times -2 plus 5. Anybody grind that out? Want to provide it in the chat? Yep, I was getting 9 as well. So our vertex is at -2, 9. All right. Found the axis of symmetry a moment ago. Parts D and E we'll do by hand. And then we'll start to draft things out in the coordinate plane. Once we have our graph, it makes it easier to identify domain, range, as well as where it's increasing and decreasing. Now to find a y-intercept, you plug 0 into your function. Okay, because a y-intercept is on the y-axis, and any point on the y-axis has an x-coordinate of 0. Does anybody want to offer the value we get when we plug 0 into the function? She'll get 5. So as an ordered pair, 0, 5. For x-intercepts, we use 0 in a different way. We set the function equal to 0. And it actually gives us an equation to solve because our function is equal to -x² minus 4x plus 5. Now the easiest way to solve this would be to factor. But before you factor anything, it might be helpful to multiply each side by -1. And that's because the coefficient of x² is a minus. Okay, so it's going to be easier to factor if the coefficient of x² is positive. Now you do distribute the -1 to clear parentheses, in which case you get x² plus 4x minus 5 equals 0. And this will factor because they're numbers that multiply to give us -5 that add up to +4. Does anybody want to maybe share in the chat what numbers those are? How about +5 and -1? So what do we do with each factor at this point? So let's set each of these to 0. Looks like we have two X-intercepts. One's going to be at -5, 0, and the other's going to be at 1, 0. Are you guys good so far? So let's start drafting some of this information into the coordinate plane. Part A, where it says opens down, this is something you check once you've sketched your parabola. And although it doesn't offer us anything to like really sketch, it is helpful, in the case where you might connect your dots, in a way that makes it face up, but your value of A says that it faces down. So in other words, part A just really helps you check your answer to a certain degree. Part B, though, gives us our first point that we can plot, -2, 9. So let's go ahead and do that. All right, so -2, 9. And this is our vertex, meaning that our axis of symmetry is going to go through that point. And I'm actually going to extend this dashed vertical line all the way across the plane. And that would be x equals -2. We have a y-intercept of 0, 5. So let's plot that. And then we have our two x-intercepts, -5, 0. And then 1, 0. I'm going to help us deduce one more point on this parabola. And I'm going to use the point 0, 5 to help us out with that. How many units away from the axis of symmetry is this point 0, 5? Yep, so the y-intercept is 2 units away from the axis of symmetry. Now keep in mind the axis of symmetry cuts it into 2 equal parts. So because there's a point that's 2 units away from the axis of symmetry at 0, 5, there's going to be a point 2 units away on the other side of the axis of symmetry as well. And that would be at -4, 5. And so I like having that extra point because it just makes it a little more accurate and helps us when we sketch this parabola, which is what I'll do right now. So I'll start at the x-intercept of -5, 0. I'll go through -4, 5, obviously the vertex, and now the y-intercept and second x-intercept. And the ends here would continue going down to -infinity, so I just extend beyond the x-intercepts and put my arrowheads, and that would be our sketch of our function. Do your guys' legs hurt yet? It's leg day, the quads. All right, any questions so far in this example? Well, for the next couple of minutes, I'd like to see if maybe you can use the graph to answer parts F, G, and H. All right, now go ahead and put my answers up in just a couple minutes, and then we'll take our break. All right, so the domain is more of a memorized fact. Remember, the domain of any quadratic function is all real numbers. So for these, by default, all real numbers. The range depends on how your parabola faces as well as your vertex. So keep in mind, range represents y values. So since this parabola faces down, we have y values going further and further down to negative infinity, which would represent the smaller end of our interval notation. But there is a largest y value on this graph. And anybody want to type in what the largest y value is? It's 9. Yep. So our absolute maximum, which is also where the vertex is at 9. That would represent the other half of the range. Now, if you start at the left end of the graph and trace this from left to right, the parabola is increasing at first. And it increases using all the x values going from negative infinity up to negative 2. So where it says increasing on, we'll write negative infinity, comma, negative 2. And then decreasing from there on out. So from negative 2 all the way down to positive infinity.